Good afternoon. My name is Mitch Anthamatten. I'm a professor in chemical engineering at the University of Rochester, and I'd like to take a few minutes and tell you about some of the research that's going on in my group. My group comprises of about 5 PhD students and 3 undergraduates, and some of my students are co-advised by Professor Shal Chen, who is also a member of our department and collaborates with me on this Advanced Materials for Photonics and Lasers Center. The general theme of my research group is to develop new materials targeting specific applications that are derived by applying polymer physics, soft matter, and supramolecular chemistry. In one theme, we are developing new actively moving elastomers, such as semi-crystalline shape memory polymers like that shown here. A shape memory polymer is essentially a material that can be deformed, stretched, twisted, and then cooled to fix it in a temporary shape. And upon reheating the material, the semi-crystalline domains melt and it recovers its shape and is capable of performing elastic work onto its surroundings. So the materials we develop are specifically to store high amounts of elastic energy, and we target biomedical devices such as stents or sutures or compressive therapy is another area. We also we have developed two-way reversible shape memory materials. We call these self-stretching polymers. They're essentially films or fibers that when you cool, they elongate themselves, they stretch themselves. And when you heat them up, they contract reversibly. So what drives the stretching is the formation of crystalline domains along a particular direction. And we can use the same line of thinking and create surfaces that go from textured, where there's a relief pattern shown here, to flat. And this phenomenon can enable switchable adhesion. So there can be, at one state, the material adheres well to a substrate, and at another state, it does not adhere well, and it can delaminate from the substrate. And this could be important for transfer printing. We've shown you can use this phenomena to basically have this elastomeric stamp that can pick up particles or layers of material as an ink and deposit it when triggered, onto a target substrate in a more robust manner. We've also, a new direction is Madeline Jessica is trying to develop new two-photon printing of shape memory polymers. So we're envisioning these high-resolution structures that can be printed with a two-photon printer, which can go to submicron dimensions. And we'd like to have a shape memory effect there to do things like the switchable adhesion, but also we envision some interlocking surfaces that can interlock when they're triggered. Our lab is also working with ion-conducting polymers for anion exchange membranes. In short, we're trying to integrate hydrogen bonding groups. We have a long experience working with hydrogen bonding groups to improve the mechanical properties and water management of these anion exchange membranes. Back to AMPL. AMPL again stands for Advanced Materials for Photonics and Lasers, and this is a center that we founded here in chemical engineering a few years ago. And it brings together groups of people from optics, from chemistry, from industry as well, to collaborate on a few common themes. And our focus is materials that can control the polarization of light. And there's two projects that I'm working on that are related to AMPL. And they're both collaborations with Professor Shal Chen. The first project is to use particles and to get them to self-assemble into phases. What you're looking at here is actually not a bunch of little particles. This is an aerial view of a bunch of logs that are floating in a river. And what you notice, there are regions of the logs that show a very high degree of order. And this type of order, where they're all aligned kind of in the same direction, is called pneumatic order, and that's a liquid crystalline state. So liquid crystals are small molecules that do essentially the same thing. What we're interested in is making nanorods, and we've done this. Wenxi Zhang and Xinchuan Cheng are working on making nanorods that can undergo self-assembly in a solvent. That's called lyotropic self-assembly. And then once we've assembled them, we can remove the solvents and sinter them together. And with sintering, we found that we're able to retain some of the particle alignment. And this leads to anisotropy in a solid state material. And since they're nanoscale particles, they don't scatter light. So we can have highly transmissive anisotropic material that are birefringents. So the application could be optical wave plates, for example. And we're working also to use polymer brushes to assist that particle assembly. And in another topic, we work with a class of materials called glassy liquid crystals. Glassy liquid crystals are soft materials that they form a liquid crystalline state at a high temperature, but when they're cooled, the liquid crystalline state's preserved and they form a glassy state where they're kinetically trapped. And so we can take the ordering of a liquid crystal, the advantage of the ordering of liquid crystal, and combine that with a solid state optical properties. So here you're looking at a film that was created in 1995. Glasses have really, they're known to be very, very stable over very long times, and this is a demonstration of that. And the light from the room hits the material, the device, and it reflects from the device. Part of the light reflects, and that's why it appears green, because the green light is reflected. The structure in the material does not allow light of green wavelength to pass through the material, and that's called a stop band. And we can actually tune the pitch of the material, the organization length scale, to create different colors that are selectively reflected. It turns out, because it's a cholesteric, it forms a helical structure inside of there, that the light that is reflected is circularly polarized of one-handedness. And the light that transmits is no longer the green light, but it looks like the red light here. It transmits through the material, it hits a mirror and it's reflected, and you can see the colors different, but the light that transmits through the device is of opposite circular handedness. So these materials and devices made from them could be used for optical isolators for defense applications. So that summarizes a few topics in my group. If you are interested, you can feel free to reach out to me. Generally, I work very closely with my PhD students. I meet them about once a week. It's a very intense experience, and we have regular group meetings as well. Our lab is located in Gavitt Hall, which is about 2 or 3 minute walk from my office. I'm located in Wegmans Hall on the top floor. It's a new building. It's shared with computer science. And that sums it up. Please reach out if you have questions, and thank you for your time. Bye-bye.